hit so far, we're going to go into a little bit more detail today. The problems that you're going to be asked to do are ones similar to this on the worksheet, so let's get that handed out. You can consider this the first half of your review. All right. We'll call this applications. Don't call these word problems if you're not doing word problems. Right? We'll call them applications, so we're still not doing word problems. All right. All of these problems, you can go ahead and scratch 2 and 3 off, though we're not going to do those. Those are fun to do, and I would be happy to work with those on a separate time right now. As far as this class is concerned, we don't need to do 2 or 3. But we are going to do every other one, everyone else, 1, 4 through 10. I'm not going to do those on the board. These are going to be your study guide. Number 1, however, has just about every aspect of exponential growth and decay as we can get. Before we start out, there's a formula that you need to commit to memory. It is sometimes written with an A, sometimes written with a P. It does not matter. It's a function of time. Some function of time, whether it be the amount or the population or whatever letter you like to use, so we'll just stick with capital A, will be equal to some initial amount, A with a sub-zero, times the exponential function RT, often written with a KT. The book uses a K, I'm going to use an R. Because the A sub-zero stands for the initial amount. The R is the growth rate if R is greater than 0 and R equals the decay rate. Did I spell decay right? I think so. Decay. If R is less than 0, my question for you in a minute here is what happens when R equals 0? But let's take a look at this equation here. The book has probably written in it P equals P sub 0 e to the kt, or it might use A, I can't remember. A of t is equal to the initial amount e to the kt. I know the book uses K instead of R. I'm using R because it's actually a growth rate or a decay rate. Since it's a rate, R might give you a better understanding of what we're looking for. I'm sure I could use K to represent a rate. I could use the letter F to represent a rate. I don't care, but I like the letter R, so I think it'll help you guys too. So, notice what happens here. When R, well, let's say when R is strictly equal to 0, which it can't really be because it doesn't make any sense. If we have an initial amount times e to the 0 times t, what is 0 times t always going to be?
0.
And e to the 0 is what? 1. So for any time t, the initial amount will be the initial amount. So there'll be no growth or decay. So when the R equals 0, that's not growth or decay. It makes no sense. It's just a constant amount. So we're not going to have it grow or decay. With that knowledge, though, when R is bigger than 0, then this thing is going to start out at some initial value, and it's going to crank up, and it's going to go pretty fast. A good representation of that is if you put a few bacteria on a petri dish, come back in a few hours, and there's a lot more, isn't there? You guys ever studied biology or whatever? So bacteria grows exponentially. And it grows with some rate. The rate will be positive because it's growing. Also out there in the kind of science is this idea of decay. Things that decay. Can anybody give an example of something that decays?
Radiation.
Radiation is probably the best one. You take something that's radioactive, plutonium for example, and it will continue to decay, and it will decay for a while, and then it will completely disappear. I often sometimes refer to an example of putting ice cream out in a hot summer day. I think decays, and it decays pretty rapidly, right? So we can talk about the rates of growth and decay based on the exponential model. Either way, when it comes to one of these problems, there is generally, and I say this kind of in a general sense because most of them are this way. You can always twist a problem here and there to throw in a twist or some kind of pitfall or something, but for the most part, you're going to be looking for the initial value first, followed by finding the rate of decay or finding R. Okay? So 1, 2. This is important. Once we have the initial amount and the growth rate or decay rate, we can then answer a multitude of questions. Once I know the model, I can answer for any time t, whichever one they ask me for. And at the same time, if they don't give me the time and they give me an amount, I can solve for the time. What I need to find from all these words first is the initial amount and the rate of decay or growth. That will be the first thing we have to do. We also need to set up this model right here for every one of them. So let's start with the first one here. Let's see how that works out. For the first one, you go ahead and read the question. Kristen counts 100 aphids. I asked this in the last class, so I'll ask again, what is an aphid? Does anybody know what an aphid is? Little tiny bug, big bug, little bug?
Tiny ladybug.
Ladybug size?
No,
Oh, ladybugs eat them, so they're tiny.
You ever
Little.
taken a leaf off a plant?
Oh, those are aphids?
Yeah. And ants milk them.
Wow. So Kristen has a lot of time on her hands, and she takes out her magnifying glass and counts 100 of these aphids on 1 little square foot of alfalfa. That really is a lot of time on your hands. Okay, question. What's the initial amount? Okay, so that's not a stretch, right? The initial amount equals 100, so we could say A sub 0 equals 100. Okay, reading on. 7 days later, she counts 140 aphids. They've been busy, so let's write this down. We have it. Time equals 0, there's 100 of these things. And then at time equals 7, there's 140. I call this an observation. I know that sounds like a redundancy, but it will be good for you to know when we need an observation of some kind to determine the growth rate. Okay, without telling me, if somebody said, hey, I counted 100 aphids today, how many will there be tomorrow? I don't know how fast aphids grow. But if I have some observation, then I have a way of finding some growth rates. So that's why you'll need to have some kind of an observation on this process. Okay, they want you to write a function that represents the number of aphids after t days. Okay, we know the model. The number of aphids after t days is equal to the initial amount, E times the growth rate times time. E raised to the growth rate times time. And we actually already have the initial value, don't we? So we can clean this up even more. This is A of t is equal to 100 e to the RT. However, we still do not have enough information to ask the question of, use this function to predict the number of aphids after 10 days. I'm going to put 10 in for t, but notice I have no idea what the growth rate is at this point. How do I use the observation and this model to come up with the growth rate?
Do you divide 40 by 7 or not?
Well, let's start the whole process off. What does this side of the equation represent?
Time elapsed.
The number of aphids, right? At time equals 0, there's going to be a sub 0 or 100. At time equals to 7, there's how many? So 140 will be equal to 100 e to the r times 7 days. You see that? I know that at time equals 7 that there's 140 is my answer. Take a look at this equation. You see there's only one variable left. What is it? Remember, e is a number. E is a number. So there's only one variable left, r. So I should be able to solve for it. And this takes you right back to the worksheets you had last night or whatever it was over the weekend. How do you solve something like this? You get e all alone. So divide by what? 100. Okay. Moving over here since I'm getting low on the board. 140 divided by 100 is 1.4. The hundreds cancel away. You get equals e to the 7r. I know it says r times 7 here, but I don't like to write r7. I like to write 7r. It's just multiplication is commutative. I just spin it around, right? Matter of fact, I could probably get away with this if I wanted to. E to the 7r was therefore equals 1.4. You guys okay with that?
Yeah.
Because equality is what?
Inverse.
I'll just let you think about that. How do I solve for r?
Divide
Take the natural log of both sides. ln of e to the 7r is ln of 1.4